In the Kalman filter code that we have seen so far, it performs what I would call a batch estimate, where in one loop, one monolithic piece of code does all of the estimates for all time. And that's a little unrealistic for a battery management system application, because in practice what happens is you are constantly updating your estimate. It's more iterative than it is batch. In other words, I'm going to make a measurement of voltage and current, and then I am going to want to update my Kalman filter by one time sample, and then I'll do other stuff in my battery management system, and then I'll come back and I'll start all over again for the next time sample. So it's not all done at once like we've seen it, but it's done a step at a time. In this section, we implement code for an EKF that uses the ESC model, and moreover, the code is refactored to be more conducive to battery management. It's more representative of what you would see in a real battery management system implementation of a state estimator. In the code, we have an initialization routine, which is what you would call when you turn the vehicle on. And then we have an update routine that is called every time we have a new set of sample data. And in this case, we also have some wrapper code, which wraps all of this together. It's like the operating system or the main program loop of the vehicle that in this case is calling only the SOC estimator, but in general would be calling everything else as well, the state of health and the balancing and everything else. Let's have a look at it. This is the top level code, and here we see the first thing we do is I'm loading a cell model. This is an enhanced self-correcting cell model from a file to be used. It has all of the model parameters of resistances and capacity and all that kind of stuff in it. And in a BMS, we would be sampling voltage and current and temperature and everything, but in this case, I'm still running it on a desktop computer, so I have a data set that was from lab test experiment where the cell cycler did all that sampling for me, so I have all that information available, and I load that from a file. And the test temperature in this case was, as maybe you can tell from the file name, plus 45, positive 45 degrees Celsius. The format of the data in this file is interesting. This is actually what we used in 5710 when we talked about dynamic data files. If you examined the code for system ID closely enough, you would see it was the same then. When I load the cell dyne P25 data, it loads one structure into memory, which is called dyne data. And that structure has several fields, script 1, script 2, script 3, for different operations that we talked about at that point. We're going to use only the script 1 portion, which is the most dynamic portion of the cell test data. And in that field, there are again subfields of time and current and voltage, and also state of charge. Now, this is not something that we measure. This is something that in the lab test was calibrated, as we mentioned earlier in this chapter, by having a defined charge to 100%, and then I run my test script, whatever that is, to its end, and then I do a defined discharge down to 0% afterwards. So this point is calibrated, that point is calibrated, and I very carefully measure ampere hours in the middle, and that allows me to do Coulomb counting to get a state of charge estimate that, because it's highly calibrated, is a reasonable estimate of what the true state of charge is. Now, again, there is measurement error in that, so even though we call it truth, it basically, we would have to say it's our best knowledge of truth that we could have. And we're going to use the time current voltage data without knowledge of SOC in our Kalman filter to see what kind of estimates we get, because that's the realistic setting. And in the end, we will compare the estimate to this so-called truth SOC to gauge how well we did. I am here, delta t is the time between any two samples, and the time does not generally start at 0, but it would be nice if it did, so I say time equals time minus the first one to force the time to start at 0. For plotting purposes, really, that's all that's used for. Reserving space for state of charge estimate and bounds. Those are there because we want to plot that data later. And I do some initialization. The state of the system, we'll see what the order of this state is later on. The first state turns out to be diffusion, second is hysteresis, third is state of charge, but we don't know that here yet. We'd have to dig into some other code to find that. So the initial uncertainty matrix is given there. It's a diagonal matrix, and this is a tuning, some tuning knobs for the performance of the EKF. And by changing these, we might be able to improve or worsen how well it does. These are just starting values for you to use to think about. Sigma V, the voltage sensor, I'm setting that to 0.2, and sigma W to 1.0 in our simulation here. Now we call the initialization code, and we'll look at the initialization code in a minute, but what I'm passing to the code is the first measured voltage, so I could have a guess from that of what state of charge might be looking the voltage up on a SOC versus OCB table. I pass it temperature, I give it the initial state covariance, the sigma V and sigma W's, and the cell model being used. That was loaded in the first line. And that puts all of the information together in a convenient structure that we call EKF data that's returned to us. And this here then is going to be continuously updated. That's our kind of global data storage for the EKF routine. And that's what needs to be remembered between every time I call the EKF update process. Now we're going to enter, this is basically done at key on. Now that the key on stuff is processed, we enter our main program loop, where in this case we are updating SOC only, but in other cases we would also be updating state of health and doing cell balancing and computing power limits and energy and all that kind of stuff inside the main program loop. This can take some time. There's a fair amount of data in the test that we're going to be processing, and I like to know if the code is stuck or if it's actually doing something worthwhile. So I make a wait bar. A wait bar is simply a graphic element on the screen that fills in as time goes, as processing happens. It's like a progress bar. And the title is computing, and the initial state is 0% done. And then I go through and I update. I do my main program loop. How many times through? Well, however much data I have. So length of voltage tells me how much data there is to work with. So I measure voltage, I measure current, I set temperature, and now I update the state of charge by calling the iter EKF function, which we'll talk about shortly. I have to pass to it the voltage, the current, the temperature, the sample interval, and this data structure that was initialized by init EKF, but we update it and we pass it here, we update it, and you'll notice it's one of the outputs. EKF data is an input and an output from this process, from this procedure. The other outputs are the present state of charge estimate and the present bounds on state of charge. Then I update the wait bar. Now you don't want to update the wait bar every time through the loop because the wait bar is actually a pretty slow process. But I say if the iteration I'm on right now is evenly divisible by 1000, then I'll update it. And I'll update it to have status k over length current. So it's a number between 0 and 1. In this case, if k is at the end, I'm done. If it's at the beginning, I've got 0. Otherwise, somewhere in the middle, so it can fill in that progress bar. And that's it. At the end, I close this weight bar so it doesn't litter my screen. That is the main procedure. I'm just going through. You can see this is pretty self-contained. I'm sampling things and I'm updating the EKF, and that's really all I'm doing. And I would also update SOH and balance and power and energy here somewhere in this loop. In this case, when I'm done, I plot things. There shouldn't be really any major surprises in the plotting code, so I'm not going to focus on that here. And we'll move on to looking at the other two functions that are called. The first one is to initialize the extended Kalman filter, and the second one is to update the Kalman filter. So initializing the Kalman filter, I pass it initial voltage, initial temperature, the covariance of the state initially, sigma V, sigma W, and the cell model data structure. I set IR, the resistor current, to 0, the hysteresis to 0, the SOC at time 0. I set to my best guess as to what state of charge is from the initial voltage, assuming I'm close enough to equilibrium state that voltage is a decent estimator of SOC. It may or not be so. And while I'm doing that, I'm initializing the indices in EKF data. So IR index equals 1 is telling me that's where in the state vector xk, index 1 is going to be IR, the diffusion current. Index 2 is going to be HK. Index 3 is going to be ZK. I could have done it any other order, but that's the order I chose. And so we could be permuting these, and hopefully that would be enough. If I've written my code right, just permuting these would be enough to still have the code operate correctly, but having different ordering. The initial state then comprises the diffusion current, the hysteresis, and initial state of charge. And that is stored in ekfdata.xhat. I also store the initial covariance. I store the noise variances. We'll see what this is later, but this has to do with changing or increasing the uncertainty of the state if I have a bunch of bad measurements in a row. And the prior current I need later on, I don't know what that is, so I'll set it to 0, and the previous sign of current I also set to 0, and the model I set to model. So as you can see, init EKF is putting a bunch of data into a single structure which is convenient to pass around the code. In a real battery management system, you probably have just pass a pointer to this around in the code, so it's quite lightweight to do that, and you just have a data structure made in memory that would hold all of this information for you. Everything is initialized, ready to go. Now it's time to iterate and update the Kalman filter by one step. So iter EKF says I'll take a voltage, a current, a temperature, a sample interval, and all of the EKF data that I've stored so far. And I'll first copy some variables out of the data structure into easier variables to think about. For example, here I say model equals ekfdata.model in order to make model easier to reference. And from that model, I need to know what is the present cell capacity, hysteresis rate, hysteresis magnitude, memoryless hysteresis magnitude, time constant, resistor for diffusion currents, resistor for IR, and coulombic efficiency. And if this particular current is less than 0, I multiply it by eta. Now, we didn't consider eta when we did our derivatives. We could have. Here I am considering the coulombic efficiency when we're doing the update itself. That might not be as consistent as we would like, so probably should choose one or the other, but here I'm showing you how to run this iteration when coulombic efficiency is taken into account. The first value of current I need when I'm going through my loop is the prior value of current, not the present value, so I have to recover that from the data structure where it had been stored. Here is the previous estimation error covariance and the sensor noise and process noise covariances. Here's the previous state estimate, and these are the indices into the state structure of the diffusion and the hysteresis and the state of charge. This is where I'm updating sign of IK, the SK variable, and I do it as long as the current is not negligible, and in my case I consider Q over 100 or C over 100 rate to be the boundary between something that's negligible and something that's not. And so if the current is bigger than that in magnitude, then sine IK equals sine IK. Otherwise, I don't change it, and I just retain the previous value of sine IK. Time for step 0. This is where we are looking at B hat and A hat matrices. I define an nx variable to be the size of x hat. In this case, there's be 3 of them. And A hat is I initialize to 0 of the appropriate size, and B hat to 0 of the appropriate size also. And then at the state of charge index, A hat is equal to 1, and B hat is equal to minus delta T over 3600 Q. In this case, Q is in ampere hours. The diffusion state, the IR index, I make equal to the diagonal of RC and 1 minus RC also in B hat. And then for the hysteresis, first I make the AH bar matrix, which I call AH here, and the A hat matrix is set to that AH value, and then the B is going to be equal to, first I augment B. The actual B matrix ends up being too wide, so I add a new column onto B, which is just 0 times the previous column. So I initialize this all to zeros, and I fill in the BHK index in the right places with the appropriate content. Okay, so I have all of this. Oh, by the way, this is B hat and B are different things. In my step 1A, I will use B in order to implement the propagation of this state, and in step 1B, I will use B hat in order to implement the propagation of the covariance. And if we have a linear system, B and B hat are the same, but for a nonlinear system like this, they are different. The linear B is the same as B hat in the first column, but not in the second. In the second column, I've got this component, and then B hat actually is just one column. I may have misspoken earlier, but B hat is only one column, and that is listed here. So that was maybe the hardest part of all of this. I now go through and I say, okay, step 1A. I've made my new x hat is A hat times x hat. This A and A hat turn out to be the same, so I just use A hat. And then B times I and sine I to update the state of the enhanced self-correcting cell model to predict the present value. Sigma x, this is taken exactly out of the notes. There's no change there. And predicting the output voltage, no change there. It's the OCV function evaluated at Z and temperature using this model. The instantaneous hysteresis, the varying hysteresis, the resistor diffusion, the diffusion voltages, and the instantaneous resistance of the cell. All of that is what you would expect for this model. Then step 2A, I have to make the C hat and D hat matrices. The C hat matrix is going to be 1 tall and nx wide, The first component, or not the first, but the component corresponding to state of charge is derivative of OCV from SOC temp. And this is basically the function that I showed you in the previous section. If we're taking the derivative of OCV, I just call that function with x hat, the present prediction, as its input and the temperature in the model. And then I also fill in the other derivative components to C hat, compute sigma y and L just as you would expect. Now we compare the residual to, the residual here, or the innovation is another word for it, which is the true voltage minus the estimated voltage or predicted voltage. And this is a single output in our case. It's not multi-output, so I'm just saying, well, if the voltage error squared is bigger than 100 times the variation sigma y, that's pretty unusual. We would not expect that to happen very often. It's basically 10 standard deviations away from the mean. Then I'm going to skip this particular measurement update. I'm concerned that the state may have started wandering in my estimator, and I'd like to not update the state based on this estimate, and particularly not update the covariance of the state, so that the covariance is allowed to get a little bit bigger. So it might be a sensor error or it might be a state error. Either way, I'm going to set L to 0. Otherwise, or in any case, I make the new x hat equals old x hat plus L times the residual. And as we did in the last EKF example, I put limits on the states that make some sense physically. So the hysteresis is limited to be between -1 and 1, and the state of charge is limited to be between -5% and 105%, recognizing it is possible to over-discharge and overcharge a cell, so we allow some flexibility there, but we don't want our estimator to get too confused by going too far away from the normal range. Finally, step 2C, I update the covariance of the estimate. And we also say, well, let's check this residual again and say if r squared is bigger than 4 sigma y, which is only 2 standard deviations, which isn't too bad, but it's still fairly unusual. Only 5% of the time should we see that. Then I am going to increase my sigma x, my uncertainty of the state, to kind of allow a little bit more adaptivity in the next iteration to maybe converge onto the true state better. And I do that only to the state of charge state. Again, this is a design decision. It's not something that theory tells you that you need to do. So I say, take the state of charge variance and compute it by multiplying the previous one by this Q bump factor in the code that we saw to initialize the filter, which I think in the code was 5. Then I want to maintain robustness of this covariance. I want it to be symmetric and positive semi-definite, so I do this SVD trick, as we've seen a couple of times. And that completes one iteration of the extended Kalman filter, and I need to store some data pertaining to that into the structure for next time. So I store the present current into the prior current variable, because next time around it will be the prior current. I store the covariance, I store the state, I set state of charge equal to the state of charge state, and the state of charge bounds to be 3 sigma bounds from the filter. And remember that these are outputs, and all of EKF data is also an output from this function directly. So there you go. We have a wrapper code which does some loading of data, but in practice that's the operating system main loop of my battery management system. I have an initialization procedure which sets up the data structure that's used by the EKF iteration, and then every time sample we call this EKF iteration to update the, the data file, the data structures. In this example, the EKF was executed for a test having a lot of dynamic profiles. So each kind of bump in this test is one UDDS profile, and then there's a bit of a rest in between. So there's quite a few of them. You can count them. There's probably around 20 inside of this test. I start with 100% state of charge and go down to around 10% state of charge before the test is finished. The solid green line in the left-hand plot is the true SOC as determined by that careful calibration process that we talked about. And the solid blue line is the EKF estimate, and the thin blue line is the EKF bound. The left picture shows us that we're doing pretty well, roughly speaking, and the right picture gives us a better idea. It's much easier to read the right picture. It's the state of charge error rather than state of charge. Ideally, the error would be 0. In this case, we see it is not. This is the error signal here, and these are the error bounds. And the error should be between the error bounds. And after a certain point, the error does wander outside of the bounds somewhat. I did a little bit of investigation. I found that the root mean squared SOC estimation error was 1.2%, which is not bad. The percent of time the error is outside of bounds is about 24%, and that's not good. So it means that the bounds, although they're pretty close to being reasonable most of the time, at least in this example, there's some concerns that I can't use the bounds aggressively as limits of SOC to be able to compute power or energy or other things that I might want to use to compute from SOC inside of a vehicle or application. In any case, we have now seen how to implement an extended Kalman filter using enhanced self-correcting cell model. And we've looked at one example from real lab test data, and we get pretty good results. It's possible to get better results, though, and the approach that we're going to look at next is called sigma point Kalman filtering, and it's derived in quite a different way from the extended Kalman filter, and in fact it does achieve or is able to achieve better results. So without further ado, let's start looking at those topics.